Hello. So now we are going to talk a bit about AMD SEV. That's the best place to discuss about AMD technology, I guess. Well, this is something that many companies ask us, do you support that? Do you support that? So at some point, we need to work seriously on it. So AMD SEV is a big topic, a lot of stuff to discuss, a lot of implications in Xen. So let's start. So first, let me introduce briefly myself. So I work in at Vates in the XCP-ng hypervisor team. So working on many things. I work on Xen since 2023. First on PV IOMMU, on paravirtualizing the IOMMU for complicated problems. It's still ongoing, but well, we are busy on SEV now. And now on SEV since this year. That's been started a bit earlier, but now we work a bit on the complicated SEV stuff. So let's start. So what is SEV, or secure encrypted virtualization? So it's the AMD implementation of confidential computing. So the idea is that the guest is encrypted, and the hypervisor cannot know what's going on in the guest. Well, not completely, but at least the data, which is confidential, is protected by the hardware. And well, we protect the guest data from the hypervisor. By default, everything in the guest should be encrypted, unless we want to share it with the hypervisor, the DOM0, or something else. So in other words, it's encrypted VMs, and the guest decide what is shared through something named the CBIT, which we put in the patch tables. So the CBIT says this is private, encrypted, well, whatever we name that, and without the CBIT, it's not encrypted. So it's built on top of some security AMD technologies like AMD SEV, which is a memory encryption engine. Well, plain SEV just encrypts the memory between the CPU and the memory. And the security coprocessor, well, PSP, ISP, I don't know exactly which is the right acronym. So SEV comes in multiple variants. Not sure exactly. Well, each variant introduces new features. So there is plain SEV, which just encrypts the guest memory. SEV encrypted states, which also encrypts the guest registers, and things start to get complicated. SEV SNP, which adds even more integrity features, which makes things even more complicated. And SEV TIO, which is a bit different. It's for doing some PCI pass-through with trusted devices using some PCI Express extension. So let's discuss a bit more on how things is gonna work with Xen. So well, the first step is we initialize everything, enable SME, or maybe just check if it's actually enabled. Initialize the PSP, check if SEV is actually supported. And then when we create a guest, we coordinate the creation of the guest with the PSP. So we need to say to the PSP, I want to create a SEV guest. And for that, we need to give to the PSP what ASID are we gonna use for this guest. Because the ASID of the guest is bound to the encryption key. And well, this is already something we are going to have issues with Xen, because Xen has a pretty specific way of handling ASIDs. And well, we need to do some stuff in Xen for that. We also need to add some SEV specific flags in the VMCB, but just enable SEV for this guest mostly. Then we create the guest as usual. So we populate the guest memory, add the kernel, all this kind of stuff. And then we need to ask the PSP to encrypt the initial guest memory. So for that, we introduce a new hypercall, well, a new set of hypercalls. So for instance, here it's prepare initial memory. We can already do that at the boot of the guest, because on the guest is boot, we can't just encrypt memory from the PSP anymore. And once everything is done, we start the guest. and that's it. Well, it's a bit more complicated than that. So first, how do we start a guest in Xen? So we have something named the PVH boot protocol or HVM direct boot ABI. So does it work with SEV? So what is actually this ABI? So the CPU starts at some entry point, PVH specific entry point of the kernel. We have some register which holds some start info structure. And the CPU is in protected mode, 32 bits, without paging, and everything is identity mapped. And what Linux does at this entry point, some basic setup, and goes into 64 bits and continue boot process. So does it work with SEV? Let's check the AMD specification on that. And well, to summarize that, yes, it does. The only thing you need to consider, which is well, what we want at the end, everything in this mode is assumed being encrypted by default. Well, you can't control encryption, it's always encrypted. Well, that's good because the guest should be encrypted by default. We're just starting it, and everything is encrypted because we encrypted everything. Yes, but there's a bit more than that. So when you boot Linux with SEV, with PVH, Linux tries to jump into long mode, but the patch tables that are used are actually hard-coded in the executable, in the kernel. And they are not SEV aware. There's no specific CBit in the patch table, which is also actually hardware specific. So from the CPU point of view, everything is shared, but everything is actually encrypted. Even though there are some specific corner cases with SEV on some access are encrypted, well, not really the case for everything. So what happened is just it doesn't work. We need to do some adjustments on the patch tables before actually going into long mode. So that's actually, that is one patch I made in the Linux PVH code to do some adjustments. And that works, at least for the very early boot process. But even more than that, of course. So then we need to patch the Linux Xen code, the Linux drivers, and well, all this kind of thing, to be aware of SEV because, well, Xen store page, PV console, shared info, it's not encrypted memory of the guest, it's actually the memory coming from the hypervisor, which is not encrypted. So we need to make them as shared mappings. So there is in Linux one function named set memory decrypted to ask Linux to remove the encryption bit and make it a shared mapping. We also need to do that for the granted pages because they are shared with another domain, and we don't want them to be encrypted. Otherwise, the other domain is just not going to understand what's in the page. And well, it's already a bit complicated because when we want to use grant pages, we're in some interrupt context, stuff like that, and we can't change the CBit in this place. So the problem starts to come. So one approach for solving that is we create a patch pool of pages that are in decrypted memory in advance and distribute that to the PV drivers. So it works, at least for block device, because the netfront is a bit trickier for that. We also had a custom hypercall for debugging because debugging SEV guest without an early console is like we are blind debugging at this point. So having some early console helps quite a lot. And the complicated part is hypercalls, which is, well, we need that everywhere. And with SEV, it's complicated. So what are the hypercall in Xen and how does it work? So in Xen, most hypercall have a parameter which refers to a virtual address to a C structure. So the idea is we make an hypercall, well, like a function call in some way. We give to the hypervisor the virtual address to a structure which has the hypercall parameters. But with SEV, virtual address doesn't have a lot of meaning actually, because to actually know where the virtual address, where is actually the data, we need to walk the guest patch tables, which are encrypted. So that doesn't work. We can't patch walk encrypted patch tables. So at the end, we don't know where the parameters of the hypercode are, and well, assuming they aren't encrypted themselves. So yeah, and having to patch walk down to virtual addresses is also problematic. It's slow. Well, it's not great and doesn't work with SEV. So one approach for solving this issue, which was considered in the original design for Xen SEV, is it's not virtual address anymore, it's physical addresses. And well, that works. But implementing that in the guest is complicated because you can't trivially convert between virtual and physical. There are some corner cases everywhere. We can actually make some bounce buffer, which is decrypted in advance. We copy to the bounce buffer, convert every virtual to physical address, and do the other way. But yeah, that's a lot of boilerplate and probably not very efficient. Many corner cases and very complicated. And if you consider SEV SNP, it's either slow in the hypervisor or you have a chance to have a patch fault in the hypervisor because you made an RMP violation, because you can't write to private memory. So if the guest tricks the hypervisor into writing to private memory one way or another, it's going to be complicated. So either it's very slow or very terrible. That's not great. So one approach that I started to experiment is, well, let's change the ABI. So let's not have to refer to guest memory, but pass everything through a small set of registers, let's say 8 registers. We don't need the entire hypercode ABI, we just take a subset of it, a minimal subset, and try to make it easy to work with. So we formalize everything in YAML files. We create some tools to create systems. So we just have to, at the end, we have functions to call, and that does the hypercall with this new ABI. So that works great with SEV and also SEV encrypted state and SNP, because it works great with something named the GHCB, which is a page which is shared with the hypervisor. Because the guest register are encrypted, we need a way to make hypercalls. And this is one of ways for the hypervisor to communicate with the guest. Well, the guest to communicate with the hypervisor. So that works great, that's very fast. We don't need to page walk anymore, even from the hypervisor side. And the guest side is actually not very complicated. We just use these systems that are generated, and well, it works. But of course, it has limitations. The registers, we don't have an infinite amount of registers, and we need to have specific logic in Xen for these new hypercalls. So there is an RFC patch series in upstream, which is HVM ABI proposal, maybe HVMv2, but we'll discuss that a bit later. And well, that's it. So what's the current status? So we have plain SEV for now. We are working on SEV encrypted state, but that's a lot of work to at least figure out how we're gonna introduce that in Xen. Linux boots. Not everything works, but well, that's already pretty nice and doesn't crash immediately. So we use with the experimental fast ABI patches and some Xen SEV patches. I managed to make Belka front work, but netfront is a bit more complicated because of a weird way of dealing with ground pages, and I need to find a way to deal with that. So that's it. Do anyone have questions? I think people have questions.
Good for questions.
I wanted to ask about the PSP. I think I recall some conversation on the mailing list that the PSP is not behind an IOMMU and that someone wanted to also use it on DOM0. I think it was AMD that
Yes.
also wanted DOM0 to use it. And I think your work implements the driver inside of Xen. The PSP
Yes.
driver is inside of Xen. So is there any plans to?
Well, I don't know.
Okay.
One of the issues is
And, yeah.
For SEV,
so the answer is it's complicated. We will need a split driver for this. The thing that it was previously called the PSP, the Platform Security Processor. It's now technically called the ASP, the AMD Security Processor. The reality is it's got multiple pieces of functionality in, and there's a whole bunch of control rings that are just referenced from one ring buffer. So yeah, talking about SEV to it is one set of control rings, and that's different from the Linux driver that does crypto offload to it. But yes, yeah, DRTM's there as well now after they fixed the previous screw up. So yeah, that's going to be complicated to get working safely.
So you mentioned at the beginning how you needed to set the C bits before jumping to long mode. Just wanted to double check that you meant before enabling paging. And
for security reasons, prior to having PAE enabled, the processor will behave as if the C bit is set even when it's not, because it's not encodable outside of PAE. So when you start running the VM with paging off, it behaves as fully encrypted, which means that when you turn the page tables on, it has to match the encryption state. You must set the C bit before you activate paging. Otherwise, you are immediately you try and jump from across a ciphertext boundary.
The next question is about the shared pages, the BD rings, everything like that. At that point, I understand you have to cross the main boundary and have sort of sharing in place, or the main will be completely garbage. However, is there any means of the initially encrypted pages? Because at the end of the day, you are going to be putting secrets in those. There are means for 2 VMs per page, and how that page will be encrypted.
I don't know. Maybe some SEV SNP or specific communication primitives exist in SEV, but I'm not aware of that, at least for.
Keys before and do the encryption for the
Yeah, that could work as well.
Just you speak to some of your server folks internally.
One thing that you mentioned about blockfront, I think that you can reuse persistent grants for that, and it's going to work if you mark the persistent grants as shared. Because there are also being bound buffering already. So.
Yes, in the blockfront case, if I see SEV, I force the bounds buffer logic, so I can bring my own buffers.
Newer versions of NetFront also have some kind of protection against unwanted sharing to bound buffering. So I think that newer versions of blockfront should also be able to convert into SAV, because one of the XSAs added bound buffering to NetFront in order to protect against leaking data against malicious backends. So there's something there.
The last time I checked the NetFront code, they were using some form of custom software UTLB logic, and they have like sub-page buffers for what network packets, and I'm not sure exactly how to make that work. I haven't figured out.
I'm going to give you the reference to the XSA.
Okay,
In
so
the code, that's probably going to be easier.
yes,
And background. But I said also we are actually porting the system runs on network devices. We will use that to.
Would you share the branch between Blockfront and Netfront, or?
No. Actually, there was we had a guy who worked it. There was a series of patch series from I don't know, network branch and network. To make ACD work, this framework goes very well to encrypt the memory which is persistent and simplest way to engine event in the we go.
Hypervisor ABI. Change some mails. I think for
It's for the people.
oh, okay. I think first of all it collides somewhat with the fancy unit.
yes,
We're aware of that. We have
yes.
I'm sorry, it's not green or red, is there, right? No, not at all.
Teddy, can you just repeat the questions? I'm sorry to do that to you.
So it's related to the ABI proposal, which
Yeah, I'm sorry. So, I mean, the primary question is, do I remember correctly that you said a design session of it?
yes, I know.
Then it might be better to discuss it there.
Yes, that's what I'm waiting for actually. I haven't proposed a design session on that because that's going to be discussed at the Andrew design session. So the better moment for discussing that is at the Andrew design session because it's on the same subject actually.